To kinetics. Profiles. Let's start there. So a reaction profile. What's a reaction profile? That's where we draw something like this. Okay, so we have the reaction coordinate. This is the energy here, or the potential energy, and this is the reaction coordinate. They're labeled differently at different places. And so, for example, you saw this curve here. We did something like this in class. R goes to P, or reactants go to products. So this is what? Exo or endothermic? This is exothermic. We know because the energy is negative, it goes downwards. If it went up, so delta H is less than 0, that's exothermic. The activation energy would be right here. Okay. First of all, does this have a transition state, yes or no? It does. Where is it? At the peak. So the peak anywhere is a transition state. Does this have an intermediate? Yes or no? No. There's no intermediate here. So let me draw an example where there is an intermediate. I'll draw another graph. Same axes. Energy versus the reaction coordinate. R goes to P. Okay. First of all, is it exothermic or endothermic? Exo again. P is a lower energy than R. Okay. Is there a transition state? Yes or no? Yes, 2. Right here, remember a line with 2 kind of looks like an unequal sign. Mark means transition state. So there's 2 transition states here. Is there an intermediate? Yeah, that's this one here. Right there. That point there signifies the intermediate. Okay, so this has 1 intermediate and 2 transition states. Let's call the intermediate something just to kind of get used to it. Let's call it, I don't know, X. Okay? So, we have 2 choices here. R goes to X or X goes to P. Which one of those is the slower step? R to X or X to P? X to P. Why is that? The hump is higher. Do you see the hump to go from X to P is taller? The net difference is higher than R goes to X. So that means R goes to X is faster. Okay? Which step is the rate determining step? Let me label them so it's easier for you to answer. 1 and 2. Which one is the rate determining step? 2, that means it's the slower step. 1 or 2, which one has a numerically smaller value for the rate? 2, because it's slower, so the rate would be a smaller value. 1 or 2, which one has a smaller value for the rate constant? Also 2. If the rate is a small value, the rate constant is also a small value. Let's see, I'm running out of questions on this. Which step, 1 or 2, is kinetically favored? 1, that's correct. Because the faster one is the kinetically favored one. Okay, I'm asking the same question in like 5 different ways. Okay? Which one, step 1 or 2, is thermodynamically favored? It might be kind of hard to tell from my diagram, but do your best. Thermodynamically favored. I'd go with 2. Why is that? Yeah, the larger drop favors thermodynamics. So the larger drop favors thermodynamics. So we could say that comparatively, step 1 is kinetically favored and thermodynamically unfavored. We could also say that step 2 is kinetically unfavored but thermodynamically favored. Okay? All the last 10 questions I asked you are the same question, just worded differently. Okay, any questions before we move on? Yeah?
So why does exothermic mean it's thermodynamically favored?
Why does exothermic mean it's thermodynamically favored? Because thermodynamically favored means going to more stable products. Stable products means lower energy. Yes?
I thought that any sort of drop all would be thermodynamically favored, so wouldn't step 2 just be more thermodynamically favored?
That's right. I'll repeat what was just said. Thermodynamically favored means that, yeah, there's a drop in energy, but I was saying respect. Compare step 1 and step 2, which one is more favored? Thermodynamically, it would be step 2. But both are. Just, we're doing a comparison. Good. All right, next. Let's talk about enzymes for a second. I think that'll be the next easiest. Enzymes, oh, yeah. When we were comparing what was favored in that last question, we were comparing step 1 and step 2.
Yeah, step 1 and step 2 to start from
So, like for step 2 was starting at the intermediate and then going to the products. Where step 1 was reactants to the intermediate. Yeah. You could also compare the overall, but we weren't doing that. The overall would be R to P. Or the reverse if we wanted. We could have all kinds of fun. Yeah. So you can draw your own squiggly diagram and quiz your friends. Yeah. Okay, enzymes, it's a type of catalyst. It's a biological catalyst. A catalyst is something that accelerates a reaction. And what does a catalyst do to the activation energy? It drops it. So it decreases the activation energy, making it more kinetically favored. So thus the reaction happens faster. You can calculate that by the Arrhenius equation. Okay? If you were given, basically it'd be a plug and chug if you were given all the data to calculate it. The enzymes, we did an example of a pseudo-state hypothesis for enzymes. You wouldn't need to know any of the biological substitutions that we did, but everything else was a typical pseudo-state hypothesis, which we'll do in just a moment. And there was nothing unusual as far as that goes. Yes, first. Say that again. The adding an enzyme, the question was, is it kinetically unfavored? Adding an enzyme makes it more kinetically favored by dropping the activation energy and so speeding up the reaction. So K would go up, activation energy would go down, and rate would also be going up. So if you see in the equation there, activation energy, if it drops because it's in the denominator, K would be going up. And that means rate would be going up. Okay? All right. Okay, going back to kinetics, PSSH. I forgot who asked that question. Oh, different question.
Yeah, I have a question. So as the rate increases, is that it's getting faster and it's more kinetically?
As the rate increases, it's getting faster and thus it's more kinetically favored. Correct. Okay, who asked the PSSH question? Do you want an overview? Do you want an example? What are we talking about here? So we can do, what if we do an overview now? If people have specific examples they brought, we can do that for the specific questions. Is that what you're looking for? Okay. So, that's what we'll do. All right, for an overview of PSSH or just the reaction mechanisms, let me say this. Okay, one thing here, if I make a little schematic, things I'm looking for. Do I see somewhere where it says something as a slow step or same thing, the rate determining step? Do I see that? If so, my default is say the rate equals that step. Okay, so write the rate for that step if it says it's slow. The second thing I'm looking for, do I see a double-headed arrow anywhere? Okay, if I'm not restricted in any way, then I'm going to say the rate of that reaction equals the reverse rate of that reaction. That is the easiest way possible to get out of doing algebra. Okay? If I see nothing. So meaning they don't tell me a slow step and or I don't see a reversible step, that means I'm using PSSH. Okay? There could be other possible combinations. So for example, you saw in your homework there was a chlorine example, carbon and chlorine together. In that case there was a reversible step, but you also needed PSSH to solve it. Okay? Or another possibility is I literally tell you in the question, solve it this way. So for example, sometimes I've said, say part A, the slow step is step 2. Solve the question. In which case, usually there's a reversible step and it's pretty straightforward. Or, even though there's a reversible step, I make you use PSSH. In that case, you cannot say rate 1 equals rate 1 reverse. So if it's kind of a simple, straightforward, generally straightforward question, if I make you use PSSH, I don't want you to say rate 1 equals rate 1 reverse. Okay? This one has an inherent assumption. This one has an inherent assumption. The assumption is the other step, not this one, is slow. Or in other words, it's assuming that this step is fast. That's an inherent assumption in it. If using this one, then you're not assuming anything. So for example, let's just do a sketch kind of example. Let's say I have A plus B goes to C, and then C goes to D, for example. The intermediate is what? C. So there could be a couple ways to solve this. If I say slow, you rejoice. And then you say, okay, awesome. I'm going to say rate 1 equals rate 1 reverse. And so K1 is A times B equals the reverse, K1 prime, C. Now, if this was true, by the way, what would I be solving for? Which rate? 1 or 2? Yeah, I'm solving for rate 2, which is K2C. I know I'm solving for that because I always solve for the slow step. Now, when I did this right here, what am I going to do with this mess that I've circled? Solve for C. Why do I solve for C? It's the intermediate, and I can plug it in right there. Okay? So that's the easiest possible scenario. In this case, I tell you step 2 is slow, and then you say, okay, if that's slow, I'm going to assume that's fast. I'm going to say rate 1 equals rate 1 reverse, solve for the intermediate, and plug it into rate 2. Yeah?
I thought the intermediate was the part that didn't show up in the overall.
The question was, I thought the intermediate was the one that didn't show up in the overall reaction. You are totally correct.
So, C shows up in
The overall reaction in this case is not written. I could write it, or I could make you write it if I could, am cranky. I don't know. Okay? The overall would just be adding those 2 reactions. But these 2 steps are what's called the elementary steps. So yeah, C does not show up in the overall. The other possibility is that, let me get a different color here. The other possibility is if I don't say it's slow, I don't tell you which one's slow. So in that case, we're talking about this right here. You're going to use PSSH for sure, even if I didn't tell you that. So to do PSSH, it's solved a little bit differently. You would find the intermediate C, you do PSSH on it, and you say, well, rate of appearance equals rate of disappearance. So it appears in rate 1, and it disappears in rate 1 reverse and rate 2. And you do the same sort of thing, dot, 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 solve for C, and then what do I do when I find C? I plug it back into the same original equation. So I'm still solving for C, I'm just solving for it in a different way. Well, I'm using PSSH, and the top one saying the one that has reversible arrows, the forward equals the reverse rate. Okay, so just read the question and see what it asks for. Again, if it says the word slow, you can do it the easy way, especially if there's a reversible step. If it doesn't say the word slow, you gotta do it this way with the PSSH. Okay? Any questions on that? Yeah?
How would we know to, like, after we solve for C using the PSSH, how do we know to plug it into the rate 2?
Okay, good. How do you know to plug it into rate 2? There's a couple ways you could have known that. One is, if I don't tell you anything, you're going to pick the rate that has the product in it, or products. And the one that has the product, D, is rate 2. Or, if I think that's going to be a little ambivalent, which one it's going to be, then I will specify. So for some reason I think it would be unclear which one to pick, then I would say, find the rate for the rate of production of D, in this case. So then you would have to pick rate 2. Okay? This case is pretty clear. There's only one product. It only appears in one place. So it's fairly clear to pick 2. Okay? All right. If you have more examples, I'm happy to do those when we enter the next part. Okay, we did PSSH. Integrated rate laws. What are we looking for here? Do we want an overview? Do we want an example? Yeah? Are you going to be given the equations for first, second, third, zero, first, second order? Yeah. It's going to look something like, let's see, I'm looking on the exam booklet. No, it will look literally like this. This is my practice exam. First order, so half-life, integrated rate law, etc. You have to know how to use it, but it is there and labeled clearly for you. Okay, cool. All right, let's see. I don't know if I have any examples. I think I do. But do you want an example, or do you want, what are we looking for?
An example.
You want an example? Okay. Let me see if I have a classic example for us to do. What's this one? Oh, what is this? Yes. There's a couple ways that can be worded. This is the kind of question, they're not hard. They always are generally solved the same way. Usually they're paired with half-life. However, there are several ways that they can be worded. I'm not sure how many ways, but let's say about 5. If in your study you practice only 2 ways, and I pick one of the other 3 ways to word on the exam, it's not that it would be unsolvable, but you would just have to do more thinking. Does that make sense? It's just on the exam, you're like, oh, I haven't seen this before. Okay, I will not freak out. I will remain calm right now and use my logic. But if you're more nervous about that, it is better to have a breadth of examples that you practice in this category for sure, because of the different ways it can be worded. Okay, there's not tons of different ways, but there are different ways for this particular kind of question. So here's one. Okay, it says, calculate the concentration of cyclopropane remaining after first order isomerization to propene. It has continued at 773 Kelvin for 200 seconds. If the initial concentration of cyclopropane was 0.1 and K equals blah, blah, blah. All right, so we're going to try this example. I'm going to, because there's something written on the bottom of this slide, I have to solve this at the top. All right, so what I would do first is go to the back of the exam and look for the first order set of equations. So I'm going to write those down. Well, I know some of you are still copying this down, that's totally fine. Let me write down the equations while you're doing that. First order says this. And for fun, I'll write down the half-life, even though they don't mention it. Often, a half-life problem can be paired with an integrated rate law question. How did I know? Maybe I'll start with how did I know it was integrated rate law? Okay, first I see first order. So that's making me think maybe it is. If you see 0th, first or second order, I start thinking, I wonder if this is an integrated rate law question. Second, in all the integrated rate laws, you should see the following variables. Concentrations, times, and or rate constants. So all those are common variables. You look at the question. First, I come across a temperature. Like, okay, interesting. We'll see if I use that. We see a time. That fits with the integrated rate law. We see a concentration here at the bottom. We see a K at the bottom. So all that points to an integrated rate law kind of problem. What am I going to do? What do I do with the temperature though? Might freak you out. You see a temperature there. What do I do with that? I completely ignore it. Okay? So we can give you I could have given you the date. Okay? It's irrelevant. So we can give you excess information. You're looking for the key variables. The key variables are the time, T, the concentration, and K, the rate constant. Okay? Any extra variables are just for fun. Just because we're hanging out and we want to do stuff like that. Okay? Now, one thing, I give you it in this form. You need to be able to write it in both forms, so it's also can be written like this. That's if I put the natural logs together, and then I move the natural log over and then make it e to the minus kt. Make sure you can do that algebra to go back and forth, especially fourth, because I give you the top one, but you may need the bottom equation I wrote there. So either it's stuck in my brain because I've done this class enough, but if it's not in your brain, you need to algebraically manipulate the top equation to get to the bottom one. In this case, the bottom one is more helpful. So I'm going to solve for the concentration. This is the concentration at time t, equals initial concentration e to the minus kt. The initial concentration was 0.1. I know that because it tells me in the problem, initial concentration. E to the minus k is given 6.7 times 10 to the minus 4 per second. And then I also know the time, 200 seconds. So it's just a simple calculation. This one turned out to be, first of all, is it going to be a bigger or smaller number? Bigger or smaller number than 0.1? Smaller. It's reacting. It's going away. So it turns out to be 0.0875. What are the units? It's a concentration. And this concentration was in molar, so it better be molar. And that's my answer. This can be varied in a couple different ways. So let me try to give you a couple ways it can be varied. First of all, the time units might not match. So it could be per second in one and minutes in the other. You just need to convert. But the most common way this could be different, instead of giving you K here, it's really common for us to give you the half-life. Super common for us to give you the half-life. In that case, you would use this equation up here at the top of the screen to change to K. So we have a lot of fun giving you the half-life, and you just convert over to K and then plug into the equation. Super, super common. Okay? Yes? Would Arrhenius be part of this? It could be possible. It's not possible in the way the question is worded, but if the Arrhenius was part of this, let me write it here on the side. K equals A e to the minus EART. So if I was having a moment of inspiration and say, let's combine as many problems as possible, I could have you find K by yourself to plug into the integrated rate law, but I would need to give you temperature and the activation energy and the frequency factor, capital A. So if you see frequency factor, capital A, and I give you a number, it has to be the Arrhenius equation. There's no possible other equation that you know of. So if you see variables that match two different equations, then it's probably a combination problem. How do you know if it's the other? There's another that looks like the Clausius clapeyron. In that case, you'd have two temperatures and two rate constants involved. Yeah. And that's also, that equation's given on the back of the test. Okay, let's move this out of the way, unless there's other questions. Okay. All right.